coming today. We are delighted to have Robert Klement here to talk about interferometric view on classical BE stars, revealing close binarity. I can't even talk this morning. I guess it is early. Robert is currently a postdoc at the CHARA array, and he previously did his PhD in Brazil. We are really happy that he's agreed to join us. It's 6 a.m. where he is, so he had to get up super early, and he's had a very busy and hectic week at the observatory. So he wants us to know that if if anything's unclear, to just ask him a question. But I'm sure that your talk will be just terrific, Robert. So thank you very much for joining, everyone. Just before we start, too, if anybody has any comments about the time of these of our actual seminars and suggest an alternate time, please do. I would like to try to have these at the time that doesn't interfere with people's schedule and where the majority of people around the globe can attend. Anyway, I'll give it over to you, Robert. Take it away.
All right, thank you, Carol. Just a slight correction, I obtained my PhD in Prague, Czech Republic, but I spent some time in Brazil with Alex's group and some time in European Southern Observatory as well. Just for the record.
My apology, and I know I got your PhD, I read your PhD thesis, and I got it from Alex, so that's my fault. Sorry about that, Robert.
That's okay, no problem. Well, yeah, first of all, I would like to thank my main collaborators, my main mentors, without whom I wouldn't be able to do this. And those are mainly Stan Steffel, Alex Karsiofi, Thomas Rivinius, and Dietrich Bade. So thank you. And yeah, I would like to dive straight into it. But first of all, feel free to interrupt me at any point. This will be somewhat improvised because I didn't have as much time as I would have liked to prepare this. So anyway, hopefully we will all learn something from this. So the interferometric quest is a quest for angular resolution, which is set up for single telescope. It's set up by the diameter of the telescope, and it of course also depends on the observed wavelength. And just a little fun fact here to start is that most insects in fact see the sun as a point source because their eyes are composed of such small elements. But here I'm here to talk about stellar interferometry mostly, which combines two or more telescopes, individual telescopes, which can be which can range from simple mirrors like siderostats to full telescopes or radio antennas. And we want to simulate a large telescope in this way to achieve a high angular resolution. Here is an illustration of a seeing limited image. So in fact, even if we have large telescopes, we have atmosphere above them usually, which is smearing the image into an about 0.5 arcsecond resolution. So in fact, if we want to exploit size of telescopes larger than very small, let's say 10 centimeters or so, we need to use some other techniques to recover the angular resolution, which is called adaptive optics, which is now present on most larger scale telescopes. But even with an 8-meter class telescope with AO, we only have 50 milliarcsecond resolution. So we need to reveal a real detail on many objects, especially on stars. We need to go to longer telescopes, say 100-meter baselines to achieve angular resolution of several milliarcseconds. Now the first star to ever was measured, its diameter, was Betelgeuse. This is the biggest star on the sky, and to actually resolve this, we would need a telescope of the size of at least 3 meters or so, which was still for the whole first half of the 20th century. It was larger than the largest telescope in the world, which was 2.5-meter telescope on Mount Wilson. But Michelson and Pease succeeded in measuring the diameter of the star by attaching a support beam to the top of the 2.5-meter telescope, which you can see here. And here it looks something like this, thus forming an interferometer, which allows to measure the interference fringes and the size of the distance between the apertures at which the fringes disappear, with which they correctly arrive at the angular diameter of this star. So let me first start by just quickly going over the main principle of interferometry. This is not meant to be exhaustive technical description, but just to give you an idea of what's needed and what are the elements and what are the observables that we have here. So we have let's say we have two individual telescopes here separated by a certain baseline, and then what sets up the actual angular resolution is the projected baseline, of course, because usually we don't have a star straight at zenith. Here the angular resolution is proportional to lambda over 2 baselines. Here the factor of 2 comes from the fact that with interferometry we actually measure the visibility curve directly. So in fact we don't need to fully resolve the object to measure its size. So in fact this resolution is boosted even more in this sense. Then we have the individual telescopes, and as I just said, if we have larger apertures than very small, we preferably have adaptive optics on each individual telescope of the interferometer. In this case, this is done to increase the throughput of the whole system, because we are losing light at every reflection here, so we need to preserve as much as we can. Then the next main component is to transport the light into the beam combination laboratory so that the beam path is exactly equal. This of course needs to be compensated because the path that the light travels in each telescope is different. So we need to have something called delay lines, where we need to control the delay, the optical path length to within a small fraction of the observed lambda. And only after that we can coherently combine the beams and measure interferometric observables. And usually what happens is that there are several different beam combiners in the laboratory, which have different purposes, different science cases. So this is, we can imagine the telescope, you can imagine this as basically a double slit experiment, where the two slits are the two telescopes. And we have a point source here at infinity, and incoming front plane, perfectly coherent light incoming. And this will, understandably, create interference pattern or fringe. And here, if we have a point source, the visibility of the fringes, which is visibility is the contrast ratio of the bright to dark fringe, will be unity, because with a point source we have perfect coherence, so perfect interference. And the idea here is to so if you imagine that this point source stops being a point source and it gets to be a little larger, then the light is no longer perfectly coherent, and the fringes will not have a perfectly high contrast, and their contrast will be reduced, and they will be smeared out. And this is the principle behind which we can measure sizes of objects on the sky by looking for the decrease in visibility with increasing baseline, basically. And if the source is large enough, we can measure its size. And then the second main observable besides visibility is the phase. This is much more difficult to measure, the phase of the fringes, because this is corrupted by the atmosphere. However, there are techniques which allow us to recover the phase of the fringes too, which is very important observable in the sense, because the visibility tells us about the size of the object, but the phase tells us about the position of the objects on the sky. Here, this is illustrated if we would have a binary star, for example, or even if this would just shift from the phase center, we would see shift in the fringes. With two telescope interferometers, we are not able, in principle, generally, to recover the phase. For that, we need at least 3 telescopes to close a triangle, and then the atmospheric corruption basically cancels out for the different pairs of telescopes, and then we can recover the phase. So here we have a single baseline here, and what happens with interferometric measurements is we have several baselines at once, and each of the baselines measures one Fourier component of the sky brightness distribution. This is the principle about it, and we need to have as many baselines as possible to fill in the so-called UV plane. So this is basically, you can imagine these are the positions of the telescopes, and as they fill in the space which would be occupied by the simulated large telescope, and this coverage gets filled in as the Earth rotates, which is a big advantage. Just naturally, as time goes on, the projected baseline changes, and therefore we are obtaining different Fourier components of the sky distribution or of our target. And then if we measure sufficient number of baselines, we can recover the phase and visibility. This is just an example observable for a uniform disk star, fully resolved. So this is the so-called visibility curve. This is what we measure. We measure the decrease in the visibility with increasing baseline to obtain the size and morphology of the object. And the phase here is, there is no phase signal. Basically, this flips between 0 and pi, simply because there is no asymmetry in such an object. So there is no displacement for the phase. And finally, we arrive at what we can measure with this. The most basic thing which we can measure with two telescopes only is the size of a star or size of some object. If we can have some phase, we can study photocenter displacement. This is particularly interesting for example, rotating disks or such things, or binary companions. We can also use interferometric data for any kind of model fitting, of course, ranging from geometric models to complex radiative transfer models. And lastly, presently it's becoming finally possible with the larger number of telescopes. Currently, the highest number is 6 at CHARA, that we are able to do actual model-independent image reconstruction, so an actual imaging with a stellar interferometer. Just a very quick historic background, because I find this to be quite interesting, and this shows quite well the interplay between optical interferometry and radio interferometry. They have complemented each other, the various developments. So the idea was first suggested all the way in 19th century in the form of aperture masking, which would be that we would form an interferometer from a single aperture just by leaving its edges open, for example. And this would actually increase the capability of a single telescope to measure a stellar diameter, because we are then able to measure the visibility component directly. This is the actual aperture mask that was used to demonstrate this on an 80 centimeter reflector. And using this instrument, this guy was able to basically arrive at an upper limit on stellar diameters correctly. The upper limit he was able to derive in this case was 160 milliarcseconds, I think, which is correct because, of course, all stars are smaller than that. Then I'm just highlighting here what I already mentioned: measurement of Betelgeuse, 1921. 7 more stars were measured in this epoch, but that was all they could achieve because it was very demanding to mechanical stability, and basically they were not able to stabilize the path delay enough to be able to measure more stars here. Then sort of the radio parts took over, where there were many developments in the radio part, including the closure phases and such things, aperture synthesis by Earth rotation. Before, in the 70s, it was sort of revived the optical interferometric part with advances in technology and also knowledge of the atmospheric turbulence and such things. So it was finally possible to use separate telescopes to coherently combine light, infrared or visible in this case. And since then, there has been, of course, massive development in this area. The current main instruments still working are VLTI and CHARA. This is the current state of the art. And there are also many developments, of course, in radio with many upgrades there. And for the 2020s, there is a new optical interferometer plant under construction, MROI, and exciting upgrades ahead for both CHARA and ENPOI. So this is very much fast developing technique. I'm just quickly going to, since I'm a postdoc directly at CHARA, I just want to point out quickly some very recent developments which might be interesting to the community, I think. So CHARA is a Y-shaped array of 6 telescopes. Here we have some example UV coverage for 6 hours of observation and 2 objects with different inclination. CHARA is capable with its baseline of 300 meters, is capable of achieving sub-milliarcsec resolution, both in visible and near IR. Here I would like to quickly advertise that we have an open access for about 30 nights per semester for the worldwide community, and this is expected to double in the next, I'm not sure if in the next semester or the one after. So there is a lot of opportunity to actually get CHARA data, or at least proposed to. And here the latest development, which just happened last week actually, is that we had this instrument called MIRC-X, which is the only one actually capable of combining all 6 telescopes simultaneously. And it works in J and H band. And there is just now so happened that they installed a new beam combiner called Mystic, which operates simultaneously with MIRC-X, and this one is offered for the K band. So in fact, what's possible now at CHARA, we are able to observe simultaneously in H and K bands and have 2 sets of 15 fringes at the same time, which you can see here on the detector from the commissioning run last week. And in the future, this is expected to work simultaneously also with a visible beam combiner that is currently under construction. So this is going to be quite interesting if it works. Hopefully it will. And one of the main science goals of Mystic includes BE stars, because it should be possible at some point to do spectral interferometry at resolutions similar to gravity or so. So this opens a new window for northern BE stars in the K band in bracket gamma. And quickly, just a note from VLTI. The latest beam combiner Matisse is also potentially interesting for classical BE stars, in the sense that it opens a new window in the L band. So although BE stars are mostly unresolved in the continuum in the mid-IR, in the L band, with the resolution of 1000, we are able to study spectral interferometry of bracket alpha lines and other emission lines, which are particularly interesting for BE stars. When we compare with radio interferometry, there are the principles are very similar. The basic principles, there are some major technical differences between radio and optical. So obviously in radio, we can combine many more antennas at once than in optical. This is because in optical, we can't amplify the signal before beam combination, whereas we can do this in radio, so it is much easier than to combine many telescopes at once. Optical is more challenging also because of short atmospheric coherence times, losses at each reflection in the beam path, also the challenging optical path length equalization, and so on. So as to summarize, the optical interferometry is very challenging in terms of planning, execution, and so on. And this makes the studies of large samples still difficult. So just to keep in mind, and compared to this, radio interferometry is somewhat easier, let's say. It has a somewhat longer tradition too, so it is more routinely used. However, we have much lower angular resolution in radio, of course, because of the wavelength we observed it. So that's why it has only limited application to stellar astronomy, like studying BE stars, because simply the angular resolution is too low. There is another possibility though of very long baseline interferometry, which basically are continent-sized interferometers, and those can actually achieve the resolution comparable to optical. The two main interferometers here I will mention are VLA and ALMA, although unlike optical, there are many more arrays, there are many more radio arrays throughout the world, whereas the optical arrays, only those two big ones exist, maybe a third one employ. So there's much less competition in that sense, I guess. Let me move on to classical BE stars. So I've been trying to apply both optical and radio interferometry to BE stars and trying to see what we can learn. So classical BE stars, I'm sure I don't have to introduce much to this community, but they are rapidly rotating B stars with line emission from self-ejected Keplerian disks, and the evolution of the disk is governed by viscosity. These B stars are favorite targets for optical interferometry, one of the most favorite ones, simply because they are bright and nearby, and or a lot of them are bright and nearby, and these can be quite easily resolved by optical interferometers today. As I try to show you, the emission line spectra interferometry, which is simply interferometry with high spectral resolution. And if we can obtain interferometry of the emission line inside the emission and outside the emission, and of course in bins across the emission line, this helps us very much to assess for example, the geometry and the disk kinematics. So for BE stars, this is a particularly interesting technique. We are also able to detect asymmetries in the disk, and something which I will focus on in this talk is a detection of close binary companions. So in fact, interferometry is filling in an important gap in the coverage of other techniques that are able to detect close companions of BE stars. And in this sense, maybe optical interferometry is still kind of underused, or maybe only now it's starting, or the instrumentation is advanced enough that we are not now able to sample even larger samples for their binarity. And I will get into this in a lot of detail in just a moment. But first, I would like to just, with these 4 boxes, I would like to give my motivation for this. So as we have heard, and it is kind of a hot topic still, the rapid rotation is an essential property for disk formation, and it is currently thought that at least the most studied, or the scenario which we have most observational evidence for, I would say, is that B stars were spun up by mass transfer in closed binaries, and that is how they acquired their rapid rotation, and which is an essential property to form the disk. So this would then explain the why B stars have disks, basically. Okay. So most B stars are still actually single, in the sense we have not detected their companions. But if we can confirm their companions, they are mostly subdwarfs, which are stripped remnants of former mass donors. So this is exactly the telltale sign of the post-mass transfer binary systems. Now the question is, because subdwarfs are very difficult to detect and difficult to obtain their fundamental parameters, here interferometry can help us to obtain visual orbits, or visual in quotation marks, because this interferometric visual orbit, let's say. And subsequently, we should be able to obtain dynamical masses. But can this actually be done with current instruments? And the answer is yes, because these systems have periods of the order of months, which translates for the nearby objects, at least within a few hundred parsecs, translates to an angular separation of less than 20 milliarcseconds. And the contrast ratio is just sort of above the limit, or just at the limit of what optical interferometry is capable of. So this should be doable. And I was mentioning the MIRC-X beam combiner, which is our 6T beam combiner. And this is the instrument of choice if we were to set out to detect these companions. And I have done just that, as I will show you a little later. But first, let me go back quickly to the radio part, because I think this is kind of interesting, and this still awaits to be resolved. This problem, it's that the angular resolution in radio is too low to resolve most BE stars, and only one single BE star was actually resolved in radio to this date, all the way in the early 90s. And it was marginally resolved along its major axis to reveal the size of about 100 milliarcseconds or so. And this, in fact, is more exciting than it looks, because it was the first direct confirmation or first direct sign for a non-spherical distribution of the envelope of the BE star. Because until this point, it was still sort of ambiguous whether the envelope is a disk or whether it's more of a spherical shape. Here we have the actual azimuthally average visibility data from which this was extracted. Here you can see that the error bars, so this is the visibility decreasing with the baseline, exactly as I showed, and so they measured the decrease in the visibility, and so this is how they were able to measure the size of this BE star. But this is the only BE star resolved in radio so far. On the other hand, radio is unique in a way that we can actually exploit the interferometric array to boost the sensitivity. And even if we can't resolve our BE stars, we can at least measure the fluxes. And that's still very useful for us to study. And actually, it lets us predict the size of the disk, even without resolving it. And there are about 40 BE stars have been detected in radio to this date. And the longest wavelength was about 10 centimeters, which is a S-band at the VLA. Yeah, so as I said, most BE disks are below the current resolution limit. So this is what we expect from for the continuum emission of a BE star disk. So it is, in a general case, it is divided between an optically thick and optically thin part, the BE star disk, and as the wavelength increases, observed wavelength increases, in fact, the pseudo-photosphere gets larger and larger. This is because hydrogen opacity increases with wavelength as well. So in fact, this means that the disk appears larger and larger with increasing wavelength. And in fact, if we want to study the large outermost reaches of these disks, we have to in fact go to longer wavelengths, because with short wavelengths, we are only going to see the inner disk basically. But if we go to millimeter or radio wavelengths, there we can actually probe the outer parts of the disk. And this is an actual model for the star Beta CMI, which is a very tenuous disk, in fact. So typical BE disks are more dense than this, which would mean that the pseudo-photosphere would be larger than this for these given wavelengths. But in this case, we see that in fact, to reveal, for example, to measure a size of 40 stellar radii of the disk, we have to go all the way to radio to centimeter wavelengths, because the size of the pseudo-photosphere at 2 centimeters is exactly around 40 stellar radii. So this is the wavelength where we need to go to study the outer reach of the disk. And if we can't resolve the disk, we can still estimate its size based on the spectral energy distribution. So if we have a truncated disk like so, for example, here, then depending on the disk density for a disk radius, there will be a certain wavelength at which the SED spectral energy distribution will present a turn down, change its slope. So basically the flux excess coming from the disk will stop rising, and the slope will become parallel with the stellar photospheric flux. And this is how we can tell whether the disk is truncated. Of course, if we assume simply that the disk is truncated, there's nothing more complicated going on there. But this is how spectral energy distribution allows us to actually sort of measure the disk size. And that's what I did for a number of BE stars, or I tried to do it for all BE stars which had any radio data. And I found that the SED turndown can be found in basically all observed BE stars. What's particularly interesting is that the structure, the SED structure usually looks the same for stars that are known as binaries, as closed binaries, and stars that appear as single. And here I'm illustrating this on gamma CAS, which is a known single line spectroscopic binary. Here I'm showing the spectral energy distribution from visible through infrared, millimeter to centimeter wavelengths. So for a simple BE disk, we expect simple power law structure. So in fact, the extrapolation of the IR fluxes should be where the radial fluxes would be expected to be. But we clearly see first the turn down, but not only did we see a turn down in the SED slope, we see that later on all the way in the radial, it actually becomes parallel again with the slope in the IR. And this, although this is not a model, this is just simple fitting of the data, we can speculate that this can be a sign of a circumbinary disk in which there is a certain power law being followed, then there is a gap perhaps in the disk, and then the circumbinary part of the disk follows with a similar density follow structure, but at a much lower starting level here. This is the same plot, but this is showing only the excess flux. So this is the disk flux divided by the photospheric flux. Here we can see it even more clearly that the radial fluxes here are basically parallel with the inner disk, suggesting possible circumbinarity of the disk. And as I said, we have 26 BE stars with good coverage, and all of them show basically similar behavior. Here I have still pending, I just obtained recently data for 11 more stars, so hopefully I'm able to analyze these soon and expand this sample from 26 to 37. Another very interesting target, which I have mentioned already, is CPER. Here you can see the same excess emission plot as I showed for gamma CAS. So again, excess emission from the disk divided by the photospheric flux, so showing just the disk flux. And again, we see a sign of possible circumbinarity. But here with CPER, as I showed you just a bit back, this one has been resolved. So we can actually compare the size that we measure using the SED. We can compare it with the size measured by the VLA at 2 centimeters, which is here. And we see that there is a big discrepancy between these two results, because my model, if I expect a simple truncated model, this is the best fit model is around 100 stellar radii. And here I have their data, the visibility data that I showed, and I overplotted with my models of different disk sizes or different disk radii. And here you can see that to agree with their data, I need a disk radius of 500 stellar radii or so, instead of 100, which I'm getting from the SED fitting. So there's obviously something wrong, and I've been trying to obtain new VLA data to repeat this observation, which is now possible in a fraction of observing time, but so far it's still pending. Hopefully we will be successful this time around, because this needs to be resolved to understand what's going on here. Either the disk is small and the size measured here is maybe overestimated by the VLA, or we are looking at a large circumbinary disk, which is detected by the resolved VLA data, but it is not in fact reflected in the SED. because here we have a discrepancy that our model reproduces the observed flux, but it does not reproduce the observed size. So that means that basically the outer disk model has to be revised to explain the low flux but the large size at the same time. So this is something, this is a project that I'm working on right now as well. This is just what the circumbinary disk model might look like. This is an ad hoc model that we made, and it seems to explain some of the data pretty well. So here we have like the gap that I was describing, which is preceded by a steeper fall off, and then the disk shows up again behind the gap. I know of one other possible evidence for circumbinarity of a B disk, and that comes from evidence from some optical spectroscopy presented for HR 2142. So it's kind of interesting to compare if this could work the same way. Okay, and so that's it from me regarding the radio part. So this is still ongoing. We would like to try to obtain the star image with ALMA, possibly, because this has not happened yet either. It might be possible. Again, it is just on the limit of the angular resolution. So we'll see if we can do that. I'm working on trying to repeat these CIPER observations to resolve this discrepancy as well. Now, however, I'll go back to optical interferometry for the rest of this talk. And quickly, I will do these two historical milestones that very much confirmed our major theoretical expectations for disks and allowed us to study it in much more detail. So soon after CIPER was resolved by VLA, there was a successful similar observation done in optical interferometry, this time by MK3 optical interferometer and for Zeta Tauri, which was clearly resolved in H-alpha emission, but it remained unresolved in the continuum, meaning that the photosphere size is smaller than 1 milliarcsec, while the H-alpha emission, as you can see, is much larger than that. Now, 13 years later, another milestone. Of course, in the meantime, a lot happened as well. But here, thanks to spectral interferometry across bracket gamma, which basically gives us interferometry for each bin across the spectral line. And with this, we were able to, or they were able to confirm Keplerian rotation of the disk, a very important feature of the star disk, which is crucial to understand its nature. So this was finally unambiguously confirmed by spectral interferometry, VLTI. But one which I found to be, I mean, this is a more recent one, but this is a big one. This represents the first model-independent image of B star disk in the H-band continuum, as well as across H-alpha emission line, which you can see down here. And also, it represents the first ever detection of an SDO companion, direct detection, that is, and actually they were able to even map its orbit, which makes FIPER into double-line spectroscopic binary with full description of the orbit, including masses, dynamical masses, and so on. This is the RV curve from H-alpha and for the secondary star. And so this is a beautiful result, which sort of inspired us to try to look for binaries for other BE stars. Here I'm just going to mention that across H-alpha you can see that these are the bins. There are several bins across the emission line. You can see first from the left that we see the bluer part of the disk, which is the side that's approaching us, and then of course in the red wing of the line we see the size of the side of the disk which is receiving us. So very, very nice result here without any model. So going back to trying to detect these faint binary companions of BE stars. Of course, most such close companions are known from spectroscopy generally, and this includes the SDO companions, which most of them have been actually confirmed in ultraviolet spectroscopy. There are some difficulties with this, that first you need favorable geometry for spectroscopy. The broadened lines of the BE stars are giving you trouble. Although here we can make use sometimes of a shell absorption of the BE star to trace actually the BE star orbit. And those BE binaries that we know, most of them actually are SB1 binaries where we don't know, where we have not detected the secondary in the spectrum, and we don't know really its nature. Another technique which was widely used for binarity detection is speckle interferometry. However, this is limited to somewhat larger separations than our science case needs. So, since this is actually a single telescope technique, so it is limited to about let's say double angular resolution of the large telescopes, which is still not enough to reveal most of these sub-dwarf companions that I mentioned. However, this is still useful to map wide orbits, which can be very, very important. I will come back to this later. Finally, I have already described interferometry. It gives us separations much lower than speckle, the lowest achievable, although the contrast ratio currently is not the best. For example, compared to speckle itself, the contrast ratio is not so great here. And of course, the big disadvantage here is the observing and data processing is very demanding. There are not that many, actually. I know only of a very small number of interferometric detections of BE, of companions, the BE stars. So here we have 5 per, which is the only true close binary that has been mapped by interferometry. Because these 2 other examples, delta sun, there is only one detection. Here we have at a separation of about 70 milliarcseconds, and delta SCO, even though it's highly eccentric, it has a semi-major axis of about 100 milliarcseconds. So again, somewhat wider binary. So not that many companions are detected for BE stars. Here, just quickly. If we want, so in the ideal case, if we want to have a binary star and obtain a complete description of the system, we usually want to combine spectroscopy and astrometry, because both of these techniques are complementing each other, and basically by combining these, we can then obtain the absolute size of orbit and also the distance and masses of the components. Here I have illustrations from this very nice review of double stars with interferometry. Diagram what you need from each technique to be able to arrive at all you need. And this is for the case of SB1. So if you actually have single-line spectroscopic binary, you need a distance. You need the distance to obtain a full description of the system, whereas if you have double-line spectroscopic binary and also interferometric orbits or astrometric orbits, you don't even need the distance, because you can derive the distance from the orbital solution. And here we are, the current state of BE and sub-dwarf binaries. So currently, actually, I forgot to count them up, so I don't know how many there are, maybe 20 confirmed SDO companions to BE stars. Most of the detections have been done in UV spectroscopy with sufficient data coverage from old IUE data, and there has been a big new study, very recent, for HST, ultraviolet spectroscopy, which brought many new detections. Also, a few of them are known or suspected from optical spectroscopy. And only one of them actually is known, of course, as I've mentioned several times by now. Only Flipper was directly detected. These SDO stars are very interesting. They are, in fact, the companions of these stars are stripped remnants of massive stars, and they are generally thought to be different from the general SDO population, which is thought to be mostly the descendants of red giants. So this is slightly, probably different class of SDO stars than the general population, and these are the parameters that were obtained for them. And here we have a very interesting evolutionary track for these SDO companions, where we can see that they are expected to have maybe 3 different phases, which is the initial contraction phase, in which they are more luminous. Then they are in the helium core burning stage, which is most of them here. And then they can also enter a short-lived helium shell burning stage. And this is thought to be the case for Viper because it is overluminous. It appears to be overluminous, and this can be explained by the fact that it is in the phase of helium shell burning. And as I alluded to before, I have set about with my colleagues Doug Geis and Luc Yanwan to try to detect these companions directly with interferometry. So we started a multi-year campaign with CHARA MIRC-X to try to detect these companions, and we have a large sample of about maybe 30 B stars, where we combine known spectroscopic binaries, SDO systems and candidates, and also BE stars with truncated disk and triple systems containing BE stars. And in all these systems, we are trying to detect these additional close companions. And so the first observations for this were obtained last November, but really it has started to take off about April this year. And I have found out that it's possible to get a binary detection with less than 2 hours of observing time, including all the overheads. So this is in fact very good, I think. And I am happy to report here that I have been able to detect at least three new SDO companions, BE stars. Here I'm showing 2 examples. 60 was a confirmed case from UV spectra, but this is the first direct detection. Here you see the data. So this is a closure phase. Blue are measurements, and red is the binary fit. And the chi-squared here was improved by the binary fit from about 4.5 to less than 1. Here the flux ratio is slightly more than 1% contribution of the SDO star. Here we can see the grid of fit map, where we can see that it clearly converges to this position here, separation of about 3 milliarcseconds. You can see that this is somewhat a bigger data set than this one. This is about 40 minutes of time on source. This is about 20 minutes of time on source only for the second star 28 Cygni, which is candidate, SDO candidate. And here we can see that even with this smaller amount of data, we can still obtain a clear detection. Here the chi-square decreased from 2 to 1. So very exciting, because I already have, I think, 2, perhaps even 3 detections for each of these objects. So I'm actively mapping the orbit, and soon, probably by next year, hopefully I can have the orbits mapped out and the systems fully constrained, including the masses, dynamical masses of the 2 components. Now for the last part of my talk, I hope I still have time. I want to focus on triple systems, because these can be very interesting to study in case there is a BE stars in them. So basically, a triple system, hierarchical triple system, is simply composed of two Keplerian orbits. So there is a close binary and orbited by a very wide companion. Here we have the option. So even if we don't detect, if you imagine we don't detect one of the inner companions, but we only detect the, let's say, the brighter inner component and the outer component, we can still, in principle, measure the inner orbit. This is thanks to the so-called reflex wobble motion, which is simply, if you imagine that you have the wide orbit and you measure it as these inner two stars orbit each other, this will introduce this so-called wobble motion, this loopy curve. This is the whole curve, and this is just an example of a well-known binary star. But here you can see the wide orbit from which directly, I mean, this is the fit, so you actually fit the orbit, of course. But the data, if you have sufficient precision, which with CHARA MIRC-X, you have a precision of down to 10 microarcseconds precision, you can clearly detect this loop and therefore constrain the actual inner orbit as well without actually detecting both inner components. So this can be very powerful. And in fact, it is currently the goal of this technique, for which even a special etalon for precise wavelength calibration was constructed. And the goal of this project is to try to detect giant planets in wide binaries. So potentially very powerful method. I'm mentioning it here also because in case we have a BE star in wide binary and we can't detect its SDO companion because, for example, it is too faint, or maybe it is not an SDO companion, maybe it is a white dwarf, even fainter. Maybe we can detect these super faint companions by observing BE stars in wider binaries and detecting this tiny wobble motion. Here, the last part, this is my most recent work, just recently published on New Gemini, which is a hierarchical triple system with an outer BE star. And we studied this object for about a year at least, and we are able to in the end arrive at a full description of the triple system, including the component masses, dynamical masses, distance to the system, and so on. So in this last part, I will just describe quickly what we did here and why is it interesting. So only about 10 systems, 10 triple B systems are known to this day. So most of them actually are waiting to be studied in much more detail. And it is interesting because it opens a bit new physics in the sense that if you have an inner binary and a companion on the outer orbit, the dynamical interaction of these three bodies can get very complicated. And under certain configurations, the outer component can drive strong oscillations of the inner pair, which can lead to flipping of the inner orbit, for example, or oscillations in its eccentricity. And this can drive even mergers of the inner binary, which is thought to be a possible progenitor for various mergers like black hole or neutron star mergers. So this is potentially very, very important, this idea of a third outer component causing dramatic changes in a close inner binary orbit. Of course, these triple systems are also invaluable snapshots of massive star evolution. And in many cases, as I also alluded to, the full orbital description can be easier in triple CBEs than in binary CBEs. Classical BE stars. And here, I'm sure you'll be delighted to hear again about HR6819, which was one of the other sources of motivation for this study on New Gemini, because we initially thought that New Gemini is a clone of HR6819. This is not so in the end. Well, once again, let me just quickly show you that the HR1619 static H alpha emission and variable, for example, H delta or other absorption lines, this can be interpreted to be both a triple system containing a black hole and a simple binary system. And the recent update is that there is no update, and we are still waiting for the VLTI data, which will finally allow us to obtain the final conclusion of which of these models is the correct one. But that's it for HR1619. Back to New Gemini. So as I said, we initially thought that it's a clone of the triple model for HR1619. This is not so, even whatever HR1619 is, because, spoiler alert, New Gemini is a triple system composed of two B-type stars. One of them is rotating much faster than the other. And there is a wide BE star in a wide orbit, separated by about 8 milliarcseconds, while the inner orbit is 3 milliarcseconds. New Gemini is also, I mean, it appears to be the brightest triple BE star, so maybe the easiest system to study in this way. There's also a shell B star, which poses the advantage that we are able to use the sharp shell absorption of the H alpha line to trace the orbit of the binary, of the B star. Here, also an interesting feature, this is dynamical spectrum of H alpha. We can see that in the past there were some dramatic oscillations of the H alpha line profile, reflecting large oscillations of the disk itself. And in fact, these variations bear many similarities to some known BE binaries like Zeta Tauri and Gamma Cas, which opens the way to the BE star possibly being itself a binary, although we could not find direct evidence for that, unfortunately. So for the full solution of the triple system, we used the techniques that I was describing before: spectroscopy, number of spectra, speckle interferometry of the wide pair, because here the speckle in fact works perfectly for our purposes. Even if it has a lower precision, in fact, it has a good phase coverage. And with the large separation, this larger error is not such an issue. And finally, we obtained interferometry from CHARA MIRC-X. We have 10 astrometric points for the wide orbit and 4 astrometric points for the inner orbit. So starting with the spectroscopy, we were able to take the spectra. New Gemini was previously known as a single line spectroscopic binary. But here with these new data sets, we were able to detect also the second inner component in the spectra. You can see an example of a composite spectrum for helium 6678 line, and below it we can see the two component spectra and their radial velocities at this very exposure. And so we can see that there are two stellar components in the spectra. So with this, we are ruling out the possible presence of a black hole there. And it turns out that the second B-type star is a fast rotator, which is why it remained hidden in previous studies, because its line is simply too broad. We were able to disentangle two additional lines, helium line and magnesium line. And this is the final RV curve for the inner binary composed of two B-type stars, similar masses. You could have mentioned that you could have noticed that I was mentioning disentangling, but I showed only two disentangled components when we have 3 stars in this triple system, obviously. Fortunately, we weren't able to disentangle the H alpha line due to variability. So we, as I said, in the end, we used the shell absorption of H alpha to trace the outer orbit, to trace the orbit of the BE star, because the shell absorption originates in the circumstellar disk of the BE star. And this is then the RV curve of a BE star, revealing some eccentricity. And this is then the RV curve of the center of mass of the inner pair here. Period 19 years. here I have just for illustration. So this is the H alpha line, and it is phased with the inner period. And here it is interesting because then it appears that it shows VR variations phase locked to the inner orbit, which might make one feel that in fact the V star itself participates in the inner orbit. But this is just this is not real. This comes from the fact that the absorption components of the inner two lines move left and right, and therefore they cause the H alpha emission peaks to fluctuate from higher V to higher R with this inner orbital period. But in fact, the B star is on the outer orbit, and this is just an illusion, sort of. This is overplotted with the inner RB curve, so you can see that in fact the absorption of the H alpha line is not moving, stationary. Whereas if we phase H alpha line with the outer orbital period, you can clearly see that here the RB curve traces the absorption, the shell absorption of the H alpha line. Here I have the final astrometric solutions. This is the inner orbit with my 4 measurements. This is the outer orbit with 10 measurements here, and the rest are the spectral measurements, which are less precise but still useful to cover the whole orbit. And here is the wobble orbit, which I was showing, and this is the wobble orbit in the case of New Gemini, just for this little detail of the orbit. And so this is the AA plus B orbit. So basically, even if we did not detect the inner component here directly, we would have been able to constrain the inner orbit thanks to this wobble motion, which you can see that the precision is more than enough to detect this wobble motion here. And the final result is that all 3 components in New Gemini have very similar masses. One last task that remains to be done, and this in fact complicates things a little bit because we have a broad-lined and narrow-lined component from spectroscopy, and we have a brighter and fainter component from astrometry. And it is not straightforward to cross-identify these components with each other. What we needed to do is we had to model the disentangled line profiles after scaling them using the observed flux ratio, and in this way we arrived at a better agreement. In the sense that the lines appear similar, reflecting the similar spectral type of the components. We arrived at the conclusion that the broad line component is the fainter component, and that the narrow line component is the brighter component. This is because it is likely more evolved, so its rotation has slowed down somewhat, while it's brighter than the slightly less evolved one. And here, if we accept this cross identification, this results in coplanar orbits. Here, this might be a little hard to visualize now, but imagine that you're looking from up here, and then the dashed lines are the projections of the 2 orbits on the sky, where the red one is of course amplified by a certain factor to be visible. And the solid lines are the orientations of these orbits in space. So they are pretty much coplanar and co-rotating in this case. Of course, if this cross identification was opposite, this would mean the orbits are counter-rotating, and it would perhaps be much more difficult to explain its origin. Whereas like this, I think a plausible explanation for the origin is the origin from a primordial cloud and evolving together for all 3 components.
Robert, sorry, you're just about at the edge of your time, just to let you know.
Perfect. I'm just about to finish. Yeah. So we have the final solution of this orbit finally, of the triple system. And we are able to say something about the stability of the system and about the evolutionary state of the system, hopefully. Not much as it turns out, but something at least. So we found that in this configuration, in the coplanar case, New Gemini is well in the stable regime. It is not subject to strong Lidov-Kozai oscillations. So it is not expected, in fact, to present the strong. So the outer BE star is not expected to influence the inner binary too much in this case, in this configuration. And if we make estimates from the disentangled line profiles, if we make estimates for the effective temperature of the stars, and if we derive their absolute magnitudes, we see that they appear roughly coeval in the HR diagram. Again, suggesting that probably this system, all three components might have originated from a single place. It is, of course, an interesting question then if the BE star itself is a binary, and then whether the present-day inner binary could have had dynamical influence on the outer BE star and its possible companion in the past. So this is still a very interesting object to study, I would say. And finally, I will summarize my talk here. I wanted to advertise sort of optical long baseline interferometry here and show you that it's becoming more usable by the general community. Also, it's offered to the general community, and support is available. So I encourage everyone to try this, and we are always looking to expand our community. Radio interferometry. We are still waiting for an image of a BE star disk. Might be possible with ALMA, will be possible with the next generation VLA for sure. VLBI, very long baseline interferometry, is not very promising currently because we did in fact some simulations, but if we are able to resolve the BE disk, it appears that there is not enough flux for us to in fact detect it. So it really seems that with the VLBI, the resolution is too high for us, the angular resolution. Then I talked a lot about the detecting of the SDO companions and how it can explain the origin of BE stars. So very soon, hopefully, I will be able to get a detection paper out with these 3 new detections that I mentioned. BE stars in triple systems, very, very important and interesting to study. Lastly, New Gemini. Well, I described all of this, so I don't even have to probably repeat all of this. Again, I would like to mention that the possible closed component of the outer classical BE stars remains undetected, unfortunately. But there are still observational hints that it could still be there, and so we will hopefully be able to continue the monitoring by interferometry. Because there has been a little tiny residual in the astrometry of the outer orbit, but it was not sufficient for us to say anything conclusive. So maybe we can detect the companion at some point. Thank you very much for your attention.
Thank you, Robert. That was a terrific talk. Excellent. Thank you. Things I've interrupted everything. I just have a couple quick questions. Maybe we have gone a little bit over time, but I think we should give people a chance to ask a few questions if people want to raise their hand. Mark, maybe you could facilitate the questions, but seeing as I have the floor right now, I have a question. So I was trying to understand the Kozai leadoff oscillations compared to these, what you called, and I don't think I've ever heard the term before, this reflex wobble motion. So the Kozai, where you usually see the inclination of the disk exchanging with the eccentricity of the orbit. Can you comment a little more detail on these reflex wobble motions? Because I'm not clear on exactly what they are, physically what's happening?
Sure, it's nothing physical. Maybe this is confusing. It has nothing to do with Lidov-Kozai oscillation. The reflex wobble motion is simply an effect of astrometric measurements. So if this is the important plot here, is this one. The wobble appears only as a consequence of the fact that we measure the separation of the AA component, let's say, and the B component, which are on a wide, long period orbit. But the AA itself is orbiting around AB, so it changes its position. So as we measure the separation of AA and B, this will wobble with this orbit.
Okay.
Is that clearer a little bit?
Yes. I'd never heard that term before, and I need to go back and read that paper. So yeah, thank you for explaining that. For your 3 new detections, are they written up in a conference proceeding, or is there a reference to them anywhere?
No, so this is brand new result, basically, weeks old. So
okay, fantastic. Okay, well, I'll thank you again for a terrific talk. And I'll be quiet and let others ask their questions, if there are any. Do we have any questions? Dietrich has got his hand raised. Go ahead, Dietrich.
Yeah, thank you, Carol. What a beautiful talk. Congratulations. Really very, very nice. Lots of significant results. Perhaps if I may, one very tiny clarification. On one of your slides, you said that most BE stars are SB1 stars. I think the precise wording would be that most BE stars that are suspected to be in binaries are SB1 systems. Now, we are not yet at the point, we may still reach it. I would not exclude that, but we are not yet at the point that we can say all BE stars are SB1 binaries.
Maybe I misspoke, because I meant to say that actually I think that most BE stars are appearing still as single stars. And so what I probably meant to say is that those that are known or suspected as binaries happen to be SB1, exactly as you said. So I must have probably misspoken.
Yeah, full agreement. And as I said, a beautiful talk. Thank you.
Thank you.
Hi, good evening. Am I audible?
Go ahead.
Yeah. Hi, Robert. So I just have only one question. So in one of your slides, I remember I saw V star, which you have commented as fast rotating with the V sin I of about 250 plus kilometers per second. So can you comment on if with such a high rotation velocity is because the binary system is in any way influencing the projected rotation velocity of the V star in any way?
Well, that is,
Yeah, this one.
Sorry, can you repeat the last part of the question?
Yeah, so you have mentioned that the second inner component is a fast mid to late B-type star with a V sin of about 250. So this is, I think, slightly higher V sin range when it comes to normal B-type stars statistically. So what I'm asking is the binary or the triple system in any way influencing the normal B-type star because of which it is having such a high rotation velocity? Is it possible that way?
Yeah, well, that is very difficult to say. It probably just reflects, in this case, I think, that it was born in this way. Maybe the origins, so one of them is fast rotating and the other one is not. Okay. When it comes to V sin I, this seems to be just, for the spectral type, this seems to be below the level of when B-type stars become BE stars, so just slightly below that. Correct. But if we I mean, the current picture seems to be that the stars, the inner two stars, were both fast rotators, and one of them has slowed down. As it appears, this one is the brighter one, the narrow line one. So it appears that it used to rotate fast, but it has slowed down because it is now more evolved. So that's I guess all we can say at this point from the available data. Fortunately.
Thank you.
So if we don't have any other pressing questions, perhaps we should wrap up. We've gone a little over time. Again, Robert, thank you. Congratulations on a wonderful talk. I suspect that there aren't as many questions because you did a very nice job of explaining all the background before presenting your results. So thank you again. And thank you everyone for coming. I look forward to our next talk in September.
Okay, thanks for inviting me. My pleasure.
Have a good day and get some rest. Thank you.
I will.
Okay, bye.